Okay, so vectors. Because you have studied vectors before, so this will be just review and maybe emphasizing which one is the maybe some notes that maybe you need to also study again. Okay. So first of all, we start the vectors by learning, or maybe becomes more familiar with the space, the 3D space. So x, y, and z. Okay. So because vectors, we will know if something that has value and it has also directions, then we can define that as a vector. And I think most of the application is in physics, like you mentioned on the waves, the force, and anything that has magnitude and value, and you can describe in some physical phenomenon, right? And the simplest dimensions that we can think of is three-dimensional, right? Three-dimensional. Although probably you have also heard the fourth dimensions, which is time, right? And theoretical physics has proposed several theorems on how many dimensions in the world, and they propose also like the existence of the multiverse and etc. and etc. And I think the most maximum number that scientists has proposed is 11 dimensions, but it's not has yet to be proven yet, but it's certainly exists in theory. Okay. But let us see the 3D space. Okay, so in this coordinate, okay, I think you may also familiar with the right hand rule, right? This can be also used for explaining the axis on three-dimension system, and later on we will use the right hand rule on something called the cross product, the cross product. So right hand rule, and then another important thing is within this space we can also create a plane. Like for example, this is plane on x and z axis, so we call this an xz plane. And below here, this is xy plane, and usually we start here, xy plane, and as our starting point to learn on graphs, right? And then at the end, we have 3 planes at least to describe the whole 3D system. This is YZ plane. So it's like a room, like you imagine like in a room, right? And also, we can also to imagine a point, like for example, point here. Maybe this is created from this. So it's on P, and this is A, B, C. So it starts from maybe from here. Start from here. Let's say it's A, and then the Y is B, and Z is C. Okay, I think this is probably easy to review. But the important thing here is because we know the plane, then we can describe some surface or probably some solids that can be described within our 3 dimensions. So if I take z equal 3 or z equal 5, 6, etc. When I take this and I want to to sketch how it looks like. Usually we sketch in 3-dimension, or we can write the 3-dimension like this, R cube, like that. This means that we'll have 3-dimension with z equal 3 inside. Now, what it looks like is, if this is 3, z equal 3 here, there's a point here, then how can we describe other axes like x and y? Because it's not describing in the informations, and we are assuming that x and y will exist in infinity, so we will have a plane that is actually crossing the number 3, z equal 3. So imagine this plane is cutting the number 3, the z equal 3. Z, x, and y. Okay. And similarly, if you have like y equal 2 or x equal 3, you will have the plane that is crossing the point. Okay. So we have, or we call this as a surface. And precisely, if you move the coordinate, or you move the axis, if you rotate, and you will see through xz plane, you will see that z equal 3 is a line, right? You see from this side. Okay. This is just a line. So when we deal with the line in xy axis, usually we deal with xy axis, y equal to, it means that if you rotate those, if we look on the 3-dimension perspective, it is, the line is actually a surface. Okay? So that's how it is. Okay? And precisely, if you have x squared plus y squared equal 1, okay, we know that this is a circle in a 2 dimensions, right? This is a circle. But if you draw in 3 dimension, let's draw. So if you draw first the xy, okay, through the xy plane, this means that this is a circle here. Let me draw this as a circle, right? Okay, maybe something like that, circle, x squared plus y squared equal 1. But then, for the z-axis, similarly, we will have an infinite numbers, or any possibility for z. So we have like a cylinder. Or probably if you have probably the z is equal 3, if we make this in terms of restrictions, then the circle will likely to be just this point, 3. But maybe if this is confusing, maybe let me draw one by one. Okay, so this is the x squared y squared equal 1. And it's still continuously infinite in z-axis. And if you have x squared plus y squared equal 1, and then z equal 3, so you have these two equations that restrict your sketch, then this means that this is precisely a circle on z equal 3. Maybe it's too big. Maybe like this. Okay. And you can also tweak the restrictions. For example, you can have, this is not really equaling 1. You can have less equal 1. That's still okay. And then you can have the z is probably like that. So it means that it's a cylinder that has 0.2 and 5 for each endpoint of that cylinder. So this is equal 5, z equal 2. Okay. And similarly, if you have y equal x, if you draw 3 dimensions, then it's precisely the line here if you look on 2 dimensions. But since it's 3 dimensions, we need to extend our z-axis, and this is the plane. I think for the introduction, there's not really a problem. I think you just need to be more familiar with the terms, and if you maybe not really sure, you know the terms, maybe you can check after the course if there's some difference with maybe different language keywords, probably maybe different. Something different in probably also explanation if you want to check out your other courses notes about vectors. Okay, another set introductions that probably is quite important is the distance, okay, in 3D system. So if I set the let's say we have P1 and we have P2. This is on entirely different coordinates between two of them. So let's say this is x1, y1, and z1, and this is x2, y2, and z2. Maybe we can have some rectangular that can help us to describe how it looks like. Probably it's helping to imagine how, where's the positions. And if this is a distance here, let's say this is a distance d. Okay. The easiest way to visualize how we can get the distance is, I think, probably it's obvious that this is using a triangle here. And we know that we can find the formula for the Pythagorean. Okay. And I think I would just directly just write that the distance is equal to, so if we, each component we are looking on all the Pythagorean on each x, y, z, this will describe as x2 minus x1 squared plus, and also plus, and I don't think we really need to prove this. I think it's obvious. Now from this distance, we can also convert into a sphere. So if you draw a sphere, let's say the center is HKL. That's the standard written system for center of the sphere, and you have the sides in which you have the diameter, and you'll have P, X, Y, Z on the other hand of the radius. Okay, so if we're looking at this sphere, so this is a sphere, it's a sphere. If we are looking at this sphere, we can connect this to the distance, in which in our sphere, the distance will be the radius. And if we're looking on the formula, so the formula of the distance, or in this case the radius, we can take it as or if we want to write in terms of the formula of this sphere, we can just square this, and this become r squared. Or if the center is origin, then the formula becomes just x squared plus y squared plus z squared equal r squared. And similarly, by taking these numbers, the radius as some numbers, for example, if we have from 1 less equal the x squared plus y squared plus z squared less equal 4, which means that we have a sphere that has restrictions from radius 1 to radius 2. And it's a sphere, but it has a hollow. Okay. So if we draw sphere, maybe it's like this. So this is a hollow. Okay. Now why your probably if you read the textbook, why this particular sphere is in the explanations of the 3D space and vectors, because later on when we deal with after chapter 12, like chapter 13, 14, and 15, most of them will be described as either vectors or using 3D space to visualize some objects. Okay. Okay, that's the introductions. Okay, so the introductions of 3D space and how some formula will be also available for the 3D space. Okay, so the next section is now about vectors. Okay. So the vector itself is after the introduction of 3D space, okay, or 3D geometric space. Okay, maybe start with just some arrow like this, and let's say we have point A and point B. Usually we say that at the point A here, we call this as the initial point, and this is a terminal. And sometimes we can write this as AB with arrow, or if we name it, and you can name it if it doesn't have a name, you can name it with any variable. Maybe name it with U, the most obvious in math. Some textbook just takes this just U with a bold style writing, but in order to differentiate with other text, let me just write with arrow at above U. Okay. Well, if you read your textbook, it doesn't have any arrow on the letter. But that's okay, because in the textbook it has bold style. And we can add factors. Okay? For example, if we describe another vectors, for example, this is from B to C, and maybe this is different value, let's say V. And now if we add these two, this is U and V, which means we are just connecting the starting point and the terminal point. And we can say that this is U plus V. Or if we imagine that the vector AC is AB plus BC. It's just similar to playing some games, finding the starting point, and then you walk on and finding a way to get into the terminal point, the finishing point. And sometimes we're getting to the factor addition, so this is factor addition. I'm not particularly write like notes or some definition, because I think it's already built on your intuitions for vector. So I think I don't really need that. Okay, and sometimes we have something called the parallelogram. So if we have, for example, the so if this is U and V, we can exchange the positions, okay, as long as it remains at the same direction. So we can take this vector U on this side and vector V on this side. And it should be the same directions like that. And we will have now two connections here. And it depends on how you can solve some vector additions. There are no fixed way to solve, but it certainly have the principles. You need to start from the terminal point and ending at the start from initial point and ends at terminal points. And similarly, if you have an arrow like this, let's say this is U, and if you make it reverse, then this will be the minus U. And that's how we can subtract the factors. Okay. And also if you multiply the factors with a scalar, for example, this is U, but you need to maybe multiply with half, and this become half U. So the value will be shorter. Or in the same way, if you multiply with maybe twice as the original size, it's also okay. So it's called a scalar multiplications. Okay. Let me just write all the keywords. Okay, scalar multiplications. And then we can write the vectors as a component of a vector. So if it's, for example, if you have vector U, and let's say this U, or maybe vector A to make it similar with your textbook, then we can write, if this has three dimensions, okay. Usually the bracket will have this not this bracket, this different. This is for coordinate, this is for vectors, just to remind you. So you need to if it's asking vectors, then you need to make the bracket like this. Okay, if you make it or not clearly make it into this kind of bracket, then it will be describe the coordinate. And usually, if we have point A, for example, point A, x1, y1, and z1, and we have B, which is x2, y2, and z2. If factor AB is, we can make it into our factor A. Then factor A will be x2 minus x1, y2 minus y1, and z2 minus z1. And then we also have the magnitude of the vector, which means the value. Okay. We can rewrite this as, let me just write in terms of a1 squared plus a2 squared plus a3 squared. Let's say this is a1, a2, and a3. So this is the magnitude. Okay. Now let me add some notes on the property of factors. Okay. I believe you are already familiar with this, so I don't really need to explain more, but just to make sure that you knew of all these properties. And another term that important in vectors is the standard basis vectors. What's the standard basis vectors? This is, we describe usually using terms I. This is vector 1, 0, 0. Vector J, 0, 1, 0, and vector K. This is 0, 0, 1. And what's the implication of this standard basis vectors? It means that we can write down the vectors in terms of I, J, and K. For example, if we are having the vector A and we want to rewrite this as I plus 2J minus 5K, which means that this is actually same thing as 1, 2, and minus 5. And in a sense, the I, J, and K, I think it will help you to describe more on how it relates to the direction, especially when you deal with cross product. Okay, I think it's helpful. Okay. And then another terms is a unit vector. Unit vector is a vector whose length is 1. When, let's say, U is unit vector, it's described as, let's say, vector A divided by its magnitude value. So we will get the unit vector if you divide the vector with its magnitude value. Okay, that's all the introductions. just the vector. But in vector itself, we particular as the dot product, cross product. Okay, so we will deal with the dot product. So dot product. Let's say we have two vectors, A and B. Then the dot product of A and B, you can write A dot B like that, is equal to A1 B1 plus A2 B2 plus A3 B3. Sometimes we call for the dot product as a scalar product because the results will be a scalar. Later. And of course, if its result is scalar, it doesn't really affect it when you reverse the writing. And also, if you dot the same vector, it will result it in the magnitude value with squared. If you dot with the some addition of factors, you can separately multiply both of this. If you multiply with 0, this will be resulting 0 because scalar. And also, if you have if D is scalar, then dA dot B will be D and then A dot B, or A dot C D B. Another important of the dot product is the angle between vectors. So let the theta on this angle on the picture is the angle between vector A and vector B, and the theta itself is in between 0 to pi. So if we apply law of cosine. So you need to count all the magnitude value, okay, all these factors, and then using law of cosine, I'll just write the results. Okay, no need to prove. I think we will have the A dot B is equal with this. And from here we can rewrite in terms of cos theta. And then by looking at this formula, we also know that if we multiply this A dot B, and if this result is 0, then factors A and B are orthogonal. Meaning the theta is pi over 2, or 90 degrees. It seems simple, but it's actually powerful for future proving, especially when we deal with equation of plane in vectors. And I think from the angle also we can describe if this is, for example, this A and B and theta here, if this is pi over 2, if theta is pi over 2, then A dot B is 0, right? So what will be the, for example, if we have this, the theta is an acute angle. So A dot B will be or equal, or maybe just write a positive number. And similarly, if you have an angle that is more than pi over 2, or we say that theta is obtuse, I rarely use obtuse as a verb, so you can imagine this is theta is greater than pi over 2. This dot product will be a negative value. By the way, for chapter 13, I will try to upload maybe one video, maybe this week or next week. So before we enter the class or start in the class, so I hope you check the video first. I will try to add the introductions and some of the basic concept on chapter 13 on those videos, so we can I think because we delayed 1 or 2 weeks, so I need to make sure that we are on schedule. Okay, I think we can have a short break and we will continue later. Now, another terms in the dot product, or in our case here, because we deal with the cosine and the angles, we have something that is related, which is called the direction angles and directions cosine. Well, it's not really that essential or important. This is just to mention that if we have a vectors like this one, we will have at least 3 particular angles that establish within this vector. So vector A, for example here, we will have 3 angles, alpha, beta, and gamma. So we will see the vectors will have alpha in between the x-axis and the vector itself. It's alpha, and with the y-axis it's beta, and with z-axis it's gamma. So alpha, beta, and gamma we called as the direction angle. Now, if we are using the standard vectors, for example, to write down the cosine alpha, then this is particular as vector A dot the standard vector I, which is the x-axis. And if we can have definitions on what is A in terms of x-axis, if we define that as A1, then this will be A1 divided by A. And same thing, if we have another term for, let's say this is A2, and the same thing here, A3, we will have also cosine beta A2 over A like that, and cosine gamma will be A3 and A like that. And this is what we call, in our term, within this section, it's called the direction of cosine. And we can write down the vectors as, if we usually write A1, A2, A3 like that. We can describe this in terms of the cosine. So we can set the magnitude value of A, and then we can, or maybe we can just factor the magnitude of A, magnitude of A, and cosine alpha, cosine beta, and cosine gamma. Or we can also write in terms of so direction cosines of vector A is the component of the unit vector in the direction of the vector A. So direction angle and direction cosine. Okay, another sections, I think the last in the dot product is the projections. The projections. Okay. So the first projections we call this is the scalar projections, and the other projection is the vector projections. So we can project the vectors into other vectors as a scalar or as another vector. For the scalar one, we are also called this as a component. For example, in this case, this is called the component of vector B along vector A. Now, if you're looking on how we get this scalar, it's precisely using the cosine of this angle, right? And then turning it into scalar means that we are only looking at the length or the value of B. Okay? So we can say that this magnitude value of B cosine theta is our scalar projection. Or if we taking the dot product and written as then we can say that the component, or let me write B cosine theta is equal A dot B divided by the magnitude value of vector A. So this is the component of B along A. Now what's the difference with the vector projection? The vectors means it's the vector, it has the directions, which means it's actually if we know that the component of B along A is equal vector A dot vector B divide the magnitude of vector A, then the projection of B onto A, or let me write here, let me rephrase this vector projection of B onto vector A. Okay. We can rewrite this. Type in like there. We can rewrite this as A dot B divided by A in terms of, this is actually the scalar but multiply with the vector A divided by magnitude value of A. So then we can write down the projection as A dot B divided by magnitude value A squared and multiply with A. So basically, the vector projections is the scalar projections multiply with the unit vector A of the one that you want to project in. Right here, vector projection means scalar multiply with the unit vector. Okay, I hope you get the idea and no need to really force yourself to memorize this. Okay. If you may be confused, then start on drawing the triangle, this vector. And maybe start with the scalar projection, which means that this length is just a scalar, it's not a vector, which means that you need just to take the magnitude of the vector p, project to A, which means you need to have the cosine to make it a scalar value here. And then the vector projection means that the scalar value here you need to multiply with the unit vector of this one, which means 2. Then this formula means that the scalar multiply the unit vector A. I hope it's easy to visualize. Because sometimes I believe some students are forcing themselves to memorize this one, maybe this one. It's wasting your brain. Okay, so leave that and start developing your own theory. I think that will be better to approach rather just memorizing randomly. Just taking some time to learning how it's done, okay, from scratch. And I think it's also applicable to other courses as well, or other lectures as well. Okay. I think one of the applications in physics, if you have like angle here and then having vectors there, probably like when you deal with the work, like you have a force and then you have some angle, and then you need to know the distance that you are forcing maybe some box. And then I think that's pretty much obvious, so I don't really need to explain for that part. I think we can just skip to the cross products. I believe dot product still okay. I believe most of you still okay with the dot product. The cross product, however, we need to have more layers, especially to imagine how the direction will work. Okay. Because cross product is actually why does maybe the theoretical mathematicians or maybe scientists, they develop the cross product because they imagine something that is not there yet. Like, for example, we deal with the vectors, like any vectors, like maybe vectors A, right, like that. and maybe factors B, probably around here. Now, if we define these two vectors as a non-zero vector, or A, B, non-zero, okay. The mathematician, they imagine what if there are some vectors that are perpendicular to both of these vectors, which means that it can be there, it can be here, right? For example. And thus, they develop something called the cross product. Okay. So that is how we can imagine. So suppose A start with just taking some definition. Imagine it has some numbers and some directions. And suppose there are vector C. And vector C is perpendicular to A and B. And because we know from the dot product, from the cosine theta, that is, if perpendicular means that if we dot this A to C, this will be 0, and if we dot B to C, it's also 0. Okay. And now we can develop two equations from here. Okay. And then eliminate C3. You can try substitute or just eliminations. We will have, I will just go directly to the results here. Now this is a form of, if we imagine with some P, maybe P C1 plus Q C2, it's obvious that if it is equal 0, then P or the C1 is equal Q and C2 is equal minus P. Okay. So the conclusions, C1 is equal and C2 is A3B1 minus A1B3. And we substitute to equation 1 and 2. This is 1 and 2. We will get C3 is A1B2 minus A2B1. It means that we develop the three directions of the vector, three components, which are A2B3 minus A3B2 Now, this is particular. We can write that the vector C is the vector A cross vector B, and it's equal to this number. And we call this cross product. And the difference with the dot product, now we will have the result as a vector. So vector product, not scalar. But perhaps the vector itself, in terms of the product, you look on how we can formulate the numbers. I think it's better to look on, or to rewrite the form as in the matrix form. So by doing the matrix, we will see some patterns that maybe we will understand easily. We will understand easily how we can get the formulations here, which is A2, B3 minus A3, B2, and so forth. So if we deal with the vectors, or the matrix here, let's say we deal with A1, A2, A3, B1, B2, B3. And C1, C2, C3. We can rewrite this as A1, B2, B3, C2, C3 minus A2 and plus A3 and this is called the determinant, okay, the determinant of matrix. Okay, if you remember, if you have 2 by 2 matrix here, the determinant will be this B2, C3 minus B3, C2. Okay. If you have 3 by 3, and this will be the determinant. Or there are at least 3 particular forms. We take A1, and it needs to multiply the determinant here. We take A2 and multiply with negative. We take the determinant on B1, B3, C1, C3. So it is as if you are covering the row and column on those A2. And A3, same thing. Covering here, you have B1, B2, C1, C2. Okay? And we can also rewrite this as let me write this positive, negative, positive, negative, positive, negative. So we can also write this minus B1, A2, A3, C2, C3, plus B2, A1, A3, C1, C3, and minus B3. A1, A2, C1, C2. And similarly, let me move this to going up a little bit. We have C1, okay. Notice that the AB here is different from the ABC here. Okay? This is illustration of the matrix, determinant of 3 by 3 matrix. And this is for the vectors above. Okay? But you will see the forms of this form here will be similar with this determinant. So how do we apply this cross product? So usually we apply in terms of the standard factor or standard basis factors, the I, J, and K. So we can rewrite this in terms of, let's say, we have vectors A1I plus A2J plus A3K. And factor B, so if we write A cross B, we can write this in terms of I, J, K, and then A1, A2, A3, B1, B2, B3. And doing the determinant, we will have A2, A3, B2, B3. This is I minus A1, A3, B1, B3 for J, and plus B1, B2, and for K. Now perhaps some of you still think that it takes time to write down all those determinants, right? However, I will show you some steps that perhaps it will help you to calculate. Now please pay attention, maybe you haven't learned this method yet. So first thing, write down the column, 2 column IJ, and write down the same thing. Okay. Next thing is let's multiply from I here, multiply here. Okay. And J multiply with A3 B1 and K with A1 and B2. Okay, another one. Let's multiply from this B1 here to A2 K. Okay. Now the results. For the blue multiplications, we will add all of them. For the green multiplication, we will add all of them, and then we need to multiply all with negative. Okay. So this will result in A2B3I plus A3B1K plus A1B2K, and then minus, if you want to take the minus, and then adding all the terms inside. A2B1K plus A3B2K and plus A1B3J. Now let's group all of them, grouping I with I, J with J, and K with K. Now let's look on how it's formed. Okay, so A2B3 minus A3B2 and plus, or maybe minus if you want to make it minus. Or maybe let me write plus first. A3B1 minus A3B2, A1B3, sorry. And then plus okay. Is it the same as what we mentioned for A cross B? The same, right? The same. Okay, so the method is confirmed to be correct. And I'm usually using this method rather than trying to multiply and find the determinant. So this method starts with 3 by 3 and rewrite the first ij. Okay. Multiply the blue line here, multiply, and you add all this multiplication. Okay. And then minus, adding the green one. Multiply, and multiply. This, I think, faster than the original method here. And this is not in your textbook. So I believe, I think it should help you to calculate maybe faster than the usual one. Anyone learned this before? Learned it before? High school? Oh yeah. Same with me. In Taiwan also learned this, or I think half, right? I asked a few students, they say that they learn with this method. You have? You learn? Okay, yeah. So some of them learn with this. So I believe some Taiwanese also learn this method when they practice the matrix. I think it's helpful to take on this one, but be careful here. Be careful here. Usually, sometimes you forget to minus the other way around. So that's cross product. So of course, from the definition itself, the cross product, if we have A cross B, okay, we can say the A cross B is orthogonal based on its own definitions to factor A and also factor B. So we can represent the vectors, for example, if this is A and this is B. Let me draw more clearly. If this is angle theta here, if we want to make out the A and then cross B, we can have our right hand. So we can start with A and then crossing B. So if we imagine this in 3D space, it will go up. So the results within these two vectors, the orthogonal one will be here. Because remember, because the orthogonal means that two possibilities going up or going down. Depends on how you decide. But since we start with A cross B, we will have going up. If we are having from B to A, it's going down. Okay, it's going down. And then we can also apply another theorem, which is stated that we can have this A cross B, the magnitude value of A cross B is equal to magnitude of A multiplied with the magnitude of B and then multiply with sine theta. So this is theta from 0 to pi. So this means that we can calculate the length of the cross product. How do we make sure that this is okay? Let me just write similar process. First, probably take the squared on the cross product, length of the cross product. And that means that we are going to square all of this results. So write all of the terms. So we calculate all the squared. And then from here, we can take all the terms and factorize becomes because it's only a and b, and then minus the from this minus 2 we will have a1 b1 and then squared. And now from here, this will result in, this is the magnitude value squared, and magnitude value b squared, and minus, this one is the dot product. Dot product of a and b squared. And then we can set up the dot product as the with cosine formula. So let me squared, and squared like that. And then we can set up the factors factor out the a squared b squared. This will be 1 minus cosine squared theta, and by doing so we will get that the 1 minus cosine squared will be sine squared, and sine theta will be positive if theta is from 0 to pi, right? On first and second quadrants, which means that we can make sure that our square root of sine squared is positive, only positive. So it's resulting in the magnitude value of the cross product will be equal to, we squared all of them, and we have this definition. So the sine, it does come from the dot product, okay? Not from the dot product has the cosine, right? the cosine is from the geometric property, but the sine is actually from the dot product. So it's not from the geometric perspective. And another implications, if you have a cross product A cross B equals 0, what's the implications? It means that factor A and factor B are parallel. But interestingly, from this cross product magnitude, we have sine theta, right? We can apply the sine into the area of the parallelogram. So if you remember the area of triangle, we can set up the triangle in terms of sine theta. Right? We have just set random triangle. Then we can have the sine theta. So, for example, if we have the parallelogram setting, let's say B, and then this is A, and it has theta, you know that this will be B sine theta, right? And based on the triangle formula, we can take the area. But then we can imagine this becomes a parallelogram area, which means that the area is actually magnitude of A multiplied with B sine theta. And by doing so, we are actually established that the area of parallelogram is actually A cross B. So this is the area of parallelogram, area of parallelogram. So the length of the cross product A and B is equal to the area of the parallelogram. Okay, one more thing before we end the class. If we cross the standard basis factor, I cross J, it's become K. Okay? So if we take some time to look on all the possibility. And don't forget we have the negative direction as well. Then if we have J cross I, this will get negative K. As I mentioned, it's going up, and if we reverse, it's going down. Same thing when we deal with J cross K, this will be I, and K cross J will be negative I. And K cross I will be J, and I cross K will be negative J. Not necessarily to be memorized, but you can just use your right hand rules to look on that this is true. Okay? For example, J cross I. So it's J here and cross I. So it should be going there. So it should be going negative. Or K cross I. So from Z to X. It's going here and going positive. And Similarly, if you reverse it, you'll go to the negative part. Okay. I think it's better just using your right hand. This is just to remember that if you have crossing I cross j, and if you compare with j cross I, it's not equal, okay, in cross product. Okay, I think that's it for today's class. We still have a little bit section on cross product, and then we can move on to the line equations and the plane equations. Okay.